everybody. Welcome back from the break. Our next speaker is Yonatan Bisk. So Yonatan is an assistant professor at Carnegie Mellon University in LTI and works on language and robotics. And there's many other things that I probably should say that I'm forgetting, but yeah, I want to hear your hot takes. OK. Oh, and this is for you.
Sure. Thank you. All right, we'll see how much these are or not hot takes. We shall wait for slides to appear. There we go. First, if you saw me knitting yesterday, you'll see me knitting later. This is what I'm working on, so that's the answer to that question. Right now, we're actually, as you can see the beginning of an L, we're adding learning, so the next word will be learning. Anyway, so that's not what I'm supposed to talk about. I'm supposed to talk about spatial and semantic awareness in embodied LLMs. And so as a bit of an introduction first, I want to just sort of explain who the hell I am and sort of what I work on. My group is roughly categorized into three topics. So there's people who work on generalization, reasoning, stuff like this. There's people who work on robotics. And there's people who work on sort of the social collaborative aspects and uncertainty modeling. And the reason I think about these things, and part of what I would like to convince you of today, is that you should also do robotics, because it allows you to explore this entire hierarchy. And I think it exposes a lot of really interesting problems that are they're physical agents, right? So that's like part of it. And then also it exposes a lot of the difficulties that we've seen in the multimodal context and so forth that people have already brought up, but makes them very real. So I want to start with a really basic question that's going to motivate how I'm thinking about what are the problems in this space. So I have some question, where can I fill up my water bottle in this building? Now, this is not a hypothetical question. It's for all of you in this particular building. And so the question is, if I was to go up to one of you and ask, you know, this thing, like, what's going on inside of your brain right now? So what I'm assuming you're not doing is querying a metric map of this building and figuring out exactly how many centimeters you have to between each turn in order to get there. I built this yesterday, walking around the hallway. So this is where we are. So when you exit, you can decide which directions you want to go. Okay, what I think you're probably doing instead is a slightly more abstracted semantic symbolic thing where you're like, well, I kind of know where the hallway is, and then I kind of know where the bathrooms are, and those are probably near where the water is, and so forth. And then you're allowing your sort of internal planner when you are in that situation to decide what the actual action is that you're going to take. And so the idea is that there's a mismatch between, for example, in robotics, what is the easy thing for us to do versus what we as humans would prefer to do, which is to think at this sort of semantic level that's kind of matched up. And so if we want to interact with a system, we have to deal with that interface and that miscommunication. We need to be able to take, if a human is giving the instruction to a robot, it needs to understand that the human is thinking like this, not like this, until the very last minute. So I'm going to start with a piece of work that lays out some of this, and it's called Embodied RAG. And the question for me in this space is, when does space become meaningful? So when is it that it becomes worth it for you to create that new node, that new semantic unit? And why isn't it that you're doing it for every square centimeter? The second part is that if I have some representation of space, I now have to ask how to reason over it, right? So to what extent am I running a standard off-the-shelf planner? To what extent am I actually doing some sort of semantic reasoning over options? So this is not here, but this gives you an example. This is what it would look like for me to run a SLAM map. If you are, how many people know what SLAM is? OK. So simultaneous localization and mapping. So this is where I have a robot that is moving around the environment. It is using depth sensors and things like this in order to build this spatial representation of the environment. And then there's this mismatch, as I just said, between that and maybe a sort of semantic map, despite their correspondences, that would tell you things like, oh, there's an open area with sunshine and tables and chairs. There's a multifunction space, things like this. So again, we are reasoning over here. The robot is building this. And on some level, so are we, right? When we move around, we have some notion of space, and we need to be able to bridge that connection, such that when I then go to the robot, I can ask it queries at different levels of semantic abstraction. So for example, find me the stairs, that's an explicit query. You know where those are, they're right out there. And so how do I return that point and then navigate to it? Where can I buy drinks? Slightly harder. I need to understand something about the space, its function, maybe even the hours of operation for me to reason over. Well, can you describe the function of this building? It's like, I don't know, I guess presumably it's for all of us to hang out. But, maybe we can be a little more explicit than that. Those things then need to go to some agent, which has to navigate by querying this, reasoning over it, and then actually localizing and going to some location. So this is our goal. We want to have systems that are taking in abstracted natural language, building representations that align with what humans might expect, mapping it over to what actually is required in the world so that they can then actually execute. So here's kind of what this looks like. This is the old CMU coffee shop. And the idea is that inside of this, there are these kind of semantic regions. There's places where students tend to wait for their coffee order, where they place the order, where people take orders, where people make orders, things like this. I'd like to be able to then run retrieval over this system such that I can then pass it to some model to produce either that waypoint or an answer to my question. Now, we have there's a line of work that we've done on top of this. I'm not going to get into it so much. My main goal today is to put a bunch of open questions in your head and not answer any of them. So in this case, there's sort of what is the level of abstraction I should be using for all these things. This is a really simple demo just to show you that the basic infrastructure does work. It's a robot demo, so it's sped up 30 times. If you're not used to watching robot demos, there'll be much cooler ones tomorrow in Andrea's talk. But we almost always do things at faster than real time. So when we show you the demos. Okay, so then it finds this place, and what I'm not showing you is the audio where it then produces. This is the best thing I was able to find. This place serves drinks, things like this. And so we want to do this in the real world. We're going to do this in a bunch of simulation environments. We're going to ask lots of different types of questions, describing the atmosphere of this environment, the overall plant trends in the environment. Right? We want to be able to handle very abstract, underspecified questions, and then figure out where in this environment to go. The work that we're doing now that extends this looks at how do we make this an agentic framework where you are deciding how much compute you want to actually spend at any time. How complicated is this? How much should I reason over this? And I like thinking about this in a more natural setting for you, which is like, imagine that you want to get from here to some place you're going for dinner tonight. You're not actually doing the whole route planning. You're thinking about the constraints on those. You're thinking about their sort of relative locations. How are you deciding how far down that tree to go? Because if I took it to the extreme, then what you could imagine, this is some work that's under review, what you could do is you could imagine that this tree that you're building up, this hierarchy that you're building up, would include all of the affordances of every object in your environment. So that's useful in this case for a robot which wants to bring the paper towels to the kitchen counter because it has two different options for kitchen towels. One that it can reach, one that it can't, and it has two different options for where to place it, one that's free and one that's not. This may feel very obvious to you, but there is still a reasoning step that's necessary to then have the robot, this is my lab space, run around and actually execute that. So if you think about this going back to that sort of agentic question from a second ago, that sort of adaptive compute question from a second ago, it's when do I decide to reason up here? When do I decide to traverse down these trees? When do I decide to start taking physical constraints into account? And so that's a big open question for me, and that's why I started with when does space become meaningful? When do affordances become relevant? How do I decide where in this hierarchy I should be at any given time? Okay. I think that the temptation for those of us who use language models a whole ton, I started off as an NLP person before I sort of wandered towards buying robots, is that, well, if we have the right tool, if we can just reason in language, in some sense I've just argued that we should, then maybe these really big language models can just take care of it for me. So maybe what I can just do is take a bunch of trajectories, pass them through the language model, and I don't have to build explicit memory structures. I don't have to reason over some graph. That feels sort of old school. Just let the model do magic. AGI is around the corner. So I want to start off with a really simple example. This is some work that is in RAL this year. I have a cup. The cup needs to get to the other side of the laptop. I got a couple options about how I might go about doing that. I'm going to assume you don't want that one. Particularly if it's pretty full. So what we did is we collected a ton of these trajectories, and then we asked these VLMs, all of your favorite APIs that you pay monthly subscriptions for, hey, which of these is right, which of these is matching my intuition, which of these is my preference, and so forth. And the results, unsurprisingly, are that these models are not great at this. And the reason for that is because they don't really understand time. So there's going to be two issues here. One is space, one is time, small topics. So I want to help it understand trajectories. What am I going to pass in? So what I just showed you is sort of a single key point. I could do optical flow. I could do a storyboard. Most of these large language models are actually doing the storyboard. So they're taking in some video that you pass in, and they say, oh, I bet you there's like 4 key moments in this. I'll just find those key frames, and I stitch them together. Then I can just use my standard image processing, and I don't have to worry about the trajectory. But when I'm in the real world, during the examples I showed you a second ago, I actually do care about how I got there. It's not just that I got there. I care that the cup of open water went over my laptop. So if I want to be here, there's now a new question, which is, great, how do I know that this is the semantically relevant point to even be tracking to know what's, in order to build this representation? So here we have just a couple of examples. So we have the difference between going on the path versus across the path. We have, we're spreading honey on a pizza here. So, this trajectory is probably a little bit better if you like that coverage. And if you've ever brushed your hair, well, you probably have a preference as to how that's done. I did learn a lot about my students' inability to brush hair as part of this project. So I want to know what to do. I want to know where to look. And I want to be able to then use that in order to represent time. So the good news is that if I have answers to most of those questions, so if I know where to look with the right perspective, if I build a trajectory, and if I fine-tune a model, then I can do it. If I simply pass it to, this is from earlier this year, so sorry, yes, there's fancier models always. But if I pass it to these things, here's your F1 for simplicity, fine-tuning, great. In general, not. There's a bunch of little takeaways I'm not getting into. I want to leave you with one of them, though. One of the problems here is just a classic domain shift issue. So if you ask these models how to do stuff, they've seen humans do it. It turns out robots and humans don't look the same. And so actually, you can cheat by just literally taking a cutout of the gripper of the robot and putting it over the human hand in a video and training on that, and you'll do better. It literally is just overfit to a bunch of irrelevant features, and so it doesn't understand the underlying function that you're doing here. So fine-tuning is important. OK, so now you might be saying, great. Time is hard, trajectories are hard. You're saying LLMs may or may not be able to do it, but it's maybe unfair. The LLM's not really like experiencing it. It's sort of like observing it. Maybe if I put the LLM in the environment per your original task and just had it move through, then I'd be OK. Let's just let the LLM experience the environment. So if you're going to be at Culm in a couple days, my student Jacob will present this work. Earlier, we had a number of people brought up the Clever data set. So the Clever data set gives you referring expressions in a 2D image. And so the idea here is very simple. Let's just make it a real environment. It's 3D. My agent moves through the environment, and then I'm going to ask really simple questions. So this is an overhead view. We actually do render it in 3D. So this is what it actually looks like as you move through this environment. And then here's the trajectory. And then I can ask questions. I could ask, counting questions, comparison questions, temporal ordering, stuff like this, and ask how well the models do. I'll show you the results. But you know that if I'm presenting this, it's that they don't do well. So that's not interesting. Here's an example I actually think is more fun. This is a visual puzzle of sorts. So here's the environment. And we have this red sphere. And it's in the same position in the frame, but 180 degrees rotated in the environment. So it's the difference between looking this way versus this way. Now the question is, does the model know these are different spheres? If I'm asking the question, the answer is no. Duh. It thinks they're the same. So why is that? It makes actually perfect sense, right? How does a language model work? How does a VLM work? I build a bunch of tokenization out of a bunch of frames. I do attention over them, yada, yada. It's just basically a voting mechanism of all those features. OK, great. So the voting mechanism says, how much red sphereness is there in this environment. It doesn't, when moving around, when rotating, build a consistent representation of space that allows it to then reason over that. So there's a fundamental mismatch there. Because you want some numbers, here's some numbers. So this is target object ground truth, and this is the prediction divided by the ground truth. So basically, like what percentages that things get right or wrong as we have longer and longer trajectories. And basically, because we've done a lot of simple single image work in the community, things are not so bad when you're up there, and things obviously sort of get worse as you go down. We try this for a bunch of stuff. Okay, so now you're like, great. I don't know when space is meaningful. I can't pass in a trajectory. I can't embody the LLM. That's okay. I know what I'm going to do. We've heard a lot about tool use. I'm just going to take all my smarts. I'm going to put it into a tool. Then it's just going to call the tool. The tool will do the counting. And then I will be safe. The only thing the language model needs to do is reason over the use of those tools. Tools will save me. All right, so what does it mean for tools to save you? Punchline, title of the paper is Tools Fail. So what does it mean for tools to save me? Well, here's my LLM pipeline. I've got some context. I've got some tool that I have to then generate the input for. I have to select what tool I'm going to use. I'm going to get the output from that tool, and I'm going to use it. So I have to decide where are my sources of error, which are the pieces that might fail, and most importantly, when can I recover? And in an embodied setting, just as a very simple example of this, I might have an object detector. I might have an action planner. So if the object detector produces the wrong detections for what's in the environment, to what extent can my AGI model actually do something meaningful with that? So we're going to start off with the absolute simplest experiment we could possibly do. What is the thing that these models have been just trained to death on? Simple arithmetic. 2-digit arithmetic. There's so many examples on the web. It's built into, like I just discovered on my iPhone, if you type an equation and click equals, it completes it for you, which love that. And so what we're going to do is we're going to say, like, hey, I'm going to have a calculator tool that makes mistakes and see what happens for the LLM. It might be that the last digit changes. It might be that any of the digits change. It could be that I flip a positive and a negative. I multiplied 2 positive numbers and all of a sudden got a negative, things like this. These are super trivial for you, non-issues. So let's start off with how well the models do at just answering arithmetic questions before I deal with the tool. So that's the black bars here. We're including the command R models from Cohere because they were specifically trained for tool use. So like that's kind of what they're geared towards. So this, what you're seeing here is, in the black line, is just I ask it arithmetic and answers my question. And then if I give it like a perfect calculator, how much better it does. Now I'm going to introduce all of these little errors, and we're going to see what happens to my performance. So the good news is, some of the models not totally terrible, but that's mostly because they just ignore the tool entirely. The models that are sort of more geared towards tool use have substantially more degradation in their performance. So to give you a picture of what's going on, again, I've asked the model, not 2 plus 2, but basically that. It knows the answer, but then I say the calculator produced 5. And I go, oh, well, the calculator said 5, it's probably 5. And so then it moves forward with the wrong answer. Now, you're saying I'll use a bunch of chain of thought and stuff like this. And yes, we did those experiments, fine. So like here's some of those kinds of results where you basically say like, hey, the calculator might be wrong, or hey, this is like a confidence estimate for the tool, so you should calibrate how much you trust it. And things do improve based on that, but they don't achieve the performance they had beforehand when there was no tool involved. Okay, so why does this matter? Because if I'm assuming that I'm going to use a tool in an actual realistic setting, there's going to be errors in the tool. And if I'm assuming that my language model can somehow interpret the results of those tools and then correct for them or make adjustments, Andrea bet me to say the word metacognition, so that I assume the model has metacognition and understands its own. Okay, it doesn't. Obviously, it doesn't. And so it's going to fail. It's not going to be able to recover from that. And then we have these questions which are like, well, when does this become mission critical? So like, when is it actually worth making those corrections? Maybe it's okay if I, in some cases, like, well, move ahead, I can't. I'm going to hit something, or maybe picking up something. I don't know what tool. Maybe it's okay if I mistake an apple and a tomato or something like this, if it's the only red object in front of me. But I now need this question of like, how do I calibrate to use of the outputs from these systems, being able to recover from these systems? And it's not the case that I can just trust that it's going to do it. Great, so we need to understand space. We're understanding space because we're moving through it, which means we have to understand time. We don't know how to pass in a trajectory to our models. It doesn't matter if I am viewing it from afar or if I'm experiencing it. In both cases, I'm not very good at it. And even when I try to encapsulate it into a tool, to think that somehow that's going to save me, I can't actually trust my model to handle the output of that tool because things could still fail. So I've just got like failures all the way down. This is why I like robots. They always fail. You just always assume that everything will always fail. And I think that's kind of a different mindset to start from. It means that I have real ambiguity, I have real notions of consequence, I have real notions of what does it mean to try to capture context that are super hard questions, but no one expects you to succeed because the only robot you've probably interacted with was a Roomba and you yelled at it when it did the wrong thing, or a self-driving car that turned in the wrong direction on the road. And so your expectations for these systems is... And I think one of the things that's dangerous in some sense about agents is that's not our expectation. Our expectation with web agents is that they're going to work. And so we are much more willing to sort of just allow them to go and run wild and not investigate all of these places as potentially huge concerns because we're like, how hard could it be? It's just coding. That's what my undergrads do. But actually, as we've established in a bunch of the talks, those are non-trivial problems. So I want to talk about ambiguity a little bit more in terms of what it looks like in sort of a realistic context. So I'm not going to go into a ton more papers here, though I'll flash a few in front of you just for completeness. So I'm going to talk, about this one here, which is what is implied by a demonstration. I'm not going to go into this one here, but I just want to put it up to explain that this is about your audio footprint. So this is an example of like existing in an environment has side effects. I make noise, right? So the reason that I'm going to talk about this is because I think that what is tempting is that when we say there's real ambiguity or there's issues with understanding context, you say, well, I'll just constrain the environment. As if I show you exactly what to do, how could you possibly misunderstand me? Of course it's going to Okay, anyway, you get it. That's where we're going. So here's the deal. This is Vid2Robot from RSS last year. Or I don't know time. So sometime recently. So the human does something, demonstrates it, the robot needs to learn from it. So what does this actually look like? Here what we have is my student, or my former student, graduated student Vidi, doing a bunch of various demonstrations, moving things around, and then the robot has to basically take those as input in order to be able to actually move the object. And so what we're going to talk about specifically is the issue of cross-object transfer, which is that I've shown you how to do something over here, and then I'm going to present you with a bunch of objects that you know how to manipulate, and the question is, what are you going to do? So what's the correct behavior? I have just taken this can, I have turned it upright. So if I show you this cup, the correct thing to do is rotate it, probably? Okay. Do you care which way? Probably, but you didn't specify. If I show you the stapler, should I rotate it to the right so that it has a long vertical y-axis? What about the little rolling pin? So the system is very confidently doing basically all the wrong things because it's generalizing from this example without actually understanding that example. It never understood the intent of why I was doing this. It didn't have some notion of like, oh, well, actually this particular object has a canonical orientation. It has an opening and there's I don't want it to spill out and stuff like this, but that's different than these other ones. And so what's happening is that it's just taking that sort of general paradigm and applying it willy-nilly. And I think this is just very cleanly demonstrates that. Don't get me wrong, I think it's great work, but I think it really cleanly articulates this sort of ambiguity problem. So, and then the question becomes like, what's missing? So we want to actually move forward on fixing things, right? I've been sort of a downer, though. There are some nice results in these various papers. And I think that what's missing is understanding the sort of conceptual space. And so what we're doing is we're looking at the results. We're looking at the sort of phenomena on the other end and then being confused as to why it's the case that it doesn't look the way we want. Which I think we have to take a step back because that's kind of like saying, why didn't the robot read my mind? okay? Of course it can't read your mind. Of course what you just did was underspecified. Of course your notion of context wasn't sufficient. And no, I do not think that an infinite prompt is going to solve everything. There's something that we need to understand. So we've talked a lot about image editing. We've talked a lot about left-right issues and stuff like this. So let's lean into that for a second. This is some work from ECCV last year, where we simply ask, this was DALL-E 3 at the time, to generate some sort of non-canonical outputs. So we have here, we ask it for a horse riding an astronaut, no go. A mouse chasing a cat, we get the opposite. Or sort of canonically, here's some blocks world stuff, and I'd like it to do that. And of course, it doesn't generate anything at least correctly. And I know, because you all have internet-connected devices in front of you, that you've all just loaded up your favorite, coolest, newest, smartest, whatever. Yeah, exactly. Okay, so before you waste another rainforest, here is GPT from this morning with the same prompt. And again, we now have the astronaut riding the horse. We do not have a horse riding an astronaut, which in some sense is better. It used to be like 6 months ago, it would say this was an inappropriate request and just fail. I was being mean to horses or something, I don't remember. Okay, so how do I go about fixing this? So I want to start off by going down to the most basic element here, which I said is that earlier I was talking about like structure, I was talking about sort of understanding intent, other things like this. So when I have something very simple like red is left of blue, blue is left of red, I just have some orientation issues. I just have some notion of these relationships. How do I train a diffusion model? Well, this goes through my favorite little transformer. It goes into this model with I add noise, and then I generate a bunch of stuff, and I have my various losses. So you're super happy, you're training your model. So the question is, did you put the right data in? So what was the data you should have put into this model in order to make sure you get as good of an output distribution as possible? Now, what most of us are doing, out of necessity, no shade, is that we're basically just downloading the biggest frickin' thing we can off the internet, and we're just crossing our fingers it's got everything we want in it. So in this particular case, because it's controlled, I don't have to do that. So I could ask some other questions of the data. So what we're specifically going to isolate is this notion of completeness versus balance. So completeness requires that every relation has been bound with every concept across the entire data set. And then balance requires that every concept is bound with each position with equal probability. And so I can do this completeness for language and vision. I can do this for balance for language and vision. I'm going to show you some plots kind of quickly, so let me just make sure we understand what's going on here. Basically, it's just, have I seen you in the left role? Have I seen you in the right role? Have I seen you in both roles? Have I seen you with every possible pair? Have I seen you with only certain things in the other role? And the question is, what of that matters? Now, the instinct here is to say data coverage, right? So give me everything. Expand the combinatorics and just give me everything. And so relatedly, what we normally do is we look for coverage, where coverage is over that distribution, which we don't actually have the ability to enumerate. So first we're going to start with visual. So I said there's a lot of numbers here. We're just going to look at a couple. So what we're looking at is completeness for relation 1, for relation 2, for sort of the two roles here, versus a coverage statistic. So this gray one down here at the bottom has 25% coverage over that distribution. This blue one up at the top has 20% coverage over the full distribution. But it has very different notions of the roles. And so therefore, when we look at the number of concepts and how well the model generalizes, the gray one that had low coverage and low completeness is down here, and no balance, sorry. And the blue one, which has even lower coverage but has made sure to adhere to these properties, is up here. So that should be pretty intuitive, actually. If the diffusion model has never seen this object, this item, this thing in that region of the image, it cannot generate it. It has to have seen it in that place. Now, the reason I think we go astray here is because, so don't rely on coverage. The reason I think we go astray here is because this is not what the trends look like for linguistics, for the language side. So on the language side, it's not the case that it doesn't matter. So I can, really hinder something. But basically, in general, like a lot of these combinations look really good and scale really well. In other words, the symbolic sort of reasoning representations that I get from language generalize pretty solidly. And so therefore, I kind of assume that if it can handle rearranging the roles, that the diffusion model can on the other side as well. But this goes back to the whole issue of the whole talk, which is that I've always had language that sort of made sense. I always had language which I could recompose and recombine in different ways. But actually pedal to the metal, you know, like wheel to the whatever it is, tire to the road, pick whatever. When I actually have to do something, when I actually have to turn that into a real value thing because I'm generating an image, into a trajectory for this robot or whatever it might be, then I start to have all kinds of issues because those domains, those modalities do not behave the same way that language does. And we've been kind of pretending like if we just don't look too closely and we put just enough patches into the just enough parameters model, it will. And that's not the case. So here's kind of what some of the errors look like, just to give you a sense. So what you have here is the generated image for this very simple task versus the ground truth image, and then some captions. So placing a plate left of can, versus duplication issues, flipped orderings, one is missing or one is wrong, so on and so forth. So there's all kinds of little issues that arise when you don't take care of that coverage, that completeness or that balance, even if you don't have coverage. Okay, so now you're excited. You're like, great. I'm definitely leaving this talk as a roboticist. He's convinced me this is the best thing since sliced bread. There's no new problems that I need to tackle in the language domain because that's the place that everything composes and generalizes, and so I should just go over there. And so this is kind of where you are right now. So I'm not going to go into some more papers, but I am going to say, no, sorry. Even language doesn't really work. You knew that. So this is some work from iClear this year where we just tried to get language models to count, and they can't. So you teach them to count to like 25 or something like this, and you ask them for 26, and they can't. But the really depressing thing is there's this other really cool model you've maybe never heard of called an RNN, and that one works just fine. It just keeps on counting. So there's something that we maybe lost in that transition. And so then this brings up a larger question, which is in across all these domains, what does it mean for us to think about generalization? What does it mean for us to think about new domains? I was sort of like, oh, I had coverage here, I had completeness there, oh, but I didn't have it on this, or I didn't have that intent, or whatever else. We don't have an answer. We are trying to work on it. So this is some work that we're still working on called model successor functions. And the idea is that basically we maybe need to rethink stuff a little bit and to think about things from sort of an inductive standpoint. So if I think about counting, how many numbers, how high do I have to learn to count before I can count to infinity? How many combinations do I need to see of things before I can interpret that there are going to be new combinations that I'm going to be able to extrapolate based off of those? And in what ways does that differ from assumptions we've made in sort of the, whether it's continual learning or multitask learning and stuff like this? What assumptions have we made about the hypothesis space and the way it does or doesn't evolve? And in what ways is that potentially hindering us? Okay, so first of all, I didn't do any of this work, they did, so that's an important detail. He was there watching. I don't know if you saw him in one of the videos, so we'll just give him honorary supervisor. The key things, so we started off, I said, so memory is semantic. So I think the first thing is that it is both spatial and it's semantic, and the question about where that interface is non-trivial. And we have to figure out when we sort of build a new concept, and then how do we reason over those concepts. Then I want to sort of argue that reasoning is an embodied task, so that there's so much information that was lost when we tried to just take the keyframes, when we tried to just take one perspective that we really want in our models. And so we really need the systems and the models to start to merge, right? They really need to exist in the environment so that they have access to all that information, and then they can do the kinds of reasoning that we want. And that generalization is probably biased in the sense that what we need to do is induce some bias or choose some bias in the hypothesis space that actually allows us to get where we want. We've seen some of this beautifully demonstrated by other talks where we have specifically designed systems to look in and decompose these images. We need to figure out how to generalize that concept, generalize these notions of completeness, and so forth, so that we can actually figure out how to make systems work and in new environments, or to what to us seem like perhaps obvious extensions, but are not to our current models. So with that, I will close and take any questions you might have. Thank you so much.
Hey, Yonatan, very entertaining talk as always. I wanted to get your sense on, do you think we have the fundamental building blocks to, for instance, acquire spatial understanding and temporal understanding, or is this paradigm of kind of downloading VLMs and slapping some post-training and this kind of workflow, is this sufficient if we're able to do data selection and balancing and have the correct bias in our training paradigm?
Yeah, so I want to answer. So thank you, because I get to just rant off of that. No, so what I want to do is first explain a quick thing. Why is it that language models are amazing? So one of the ways I tend to think about this is I have some task. I want to represent my task. It's, whatever the domain is. The best way for me to do that would be to have the perfect basis vectors for representation, right? And now the question is, where would I get such basis vectors? Where would I get that embedding space? So what if what I did was I collected every human for the last thousands of years and had them all think about what are all the things that might be important, and then give every single one of them a name, and then have them all detail how they might interact with one another, and then I'll use that as my embedding space. That would be like a pretty good embedding space, particularly for things that are human-oriented or in human-built environments. And so that's what a language model gets to leverage, right? That's a wonderful representation space. But then that leaves open the ineffable. It leaves open the personal. It leaves open the novel, right? It's all of these things where I, as a child, sort of interact with a system differently. And so what we're hoping right now, which I don't think there's anything fundamentally wrong with, and it's potentially very useful, is that by this data scaling, by this downloading more and more stuff off the web, by maybe putting some amount of structural bootstrapping around it, that we're going to be able to solve tasks or get tasks that we're interested in to be in domain. And we should do that. I would love to buy a household robot that did, most things. But we also have to be aware that there's this. In the real world, those errors are important. So there's a reason we don't have a bunch of self-driving cars, because small errors are deaths. If we had household robot and it hasn't quite captured the physics, or your environment is slightly different, how many broken dishes are you comfortable with from your robot that's cleaning up, right? What's your sort of limit there? And so I think that sort of a roundabout answer to, yes, we should do this, we should download those things, we should actually continue to grind, but also we should be cognizant that there's just going to be a perpetually new data that's always being generated that is not going to fit that, and that may just be stuff that's in your own life or home. And so we need a different learning system if we're going to actually handle that.
Hi, thanks for the great talk. I wanted to discuss a bit further on a statement that you made in your talk, which is, not all modalities generalize as language does. I believe you were talking about it in the context of compositional text-to-image generation, and if I understood correctly, you're referring to the compositional generalization abilities of language, which other modalities don't have. So I work at the intersection of vision and language quite a bit, and I have been thinking about this a bit. Like vision is not compositional. The representations are not compositional. They're very low level. It's a perceptual modality. People have tried using different kinds of representations, such as scene graphs or object-centric representations that allow for better compositional generalizations. But clearly, that's not the state of the art, because they have problems. It's not scalable. The representations are not that rich. So yeah, I was just curious to know if, first, whether my understanding of what you were referring to is right, and second, if you had any thoughts on how can we, basically get representations from other modalities which are more compatible with language.
Yeah, no, I mean, so first of all, yes, absolutely, and second of all, I wish I had answers. I'll tell you the one thing that is on my mind, and this goes back to sort of maybe the robotics anchoring. I think so. I also worked for a long time in vision as images, and I think it's a fun domain. One of the things I think I've come to get frustrated with, specifically, I have a new student who's a neuroscience student who's been looking at like fMRIs of people looking at images and stuff like this. And it's like, how do I find compositionality in the visual domain? How do I get those representations? Is that an image is just a snapshot in time. And I think that is actually maybe hurting us. So it's like saying, I want a representation of a word, and I don't know what all the futures are that might come from it. But I'm only going to study that one thing, and I'm going to try to capture that. And so then we do scene graphs and stuff like this. Yes, we try to build these representations on top of them for some specific task. But we don't actually know what to attend to because we didn't actually see it in the appropriate context, like the temporal context. So the classic example, right, is like you've got the baseball. Whatever. I don't know if he's going to hit the ball or if he's going to switch to a bunt or what's about to happen. So I have to just make this guess, and so I'm worried we're kind of hurting ourselves by sort of limiting that. It's like if NLP was only allowed to study words, like in isolation and never in the context of a document or something like this. And so with images, we're sort of doing something similar. And so then a lot of what might be the complexities, for example, in a scene graph, we're capturing every possible predicate. And it's like, yeah, but the human wouldn't even have noticed most of those predicates because they were completely irrelevant to the 3 frames before, and they would have been erased in the 3 that came after. And so to what extent is that part of the problem, is that we're like approaching it from the wrong direction?
Thank you. Happy to chat more on this.
Yeah.
Okay, so you mentioned the learning algorithm being a problem. So what should it be?
Well, clearly rerun evolution from scratch. No. So I don't know. So what we're trying to do. So the work that I threw up very briefly, the model successor, is very much a work in progress. It's a very long document. I mean, I think my student Yingshan did a beautiful job with even the figures in it. So comments and feedback are very much appreciated. What we've been trying to do is figure out what are the assumptions we're making about hypothesis classes and data distributions within the various learning paradigms, and does a characterization like that help us come up with something that might be different? And so where we're currently landing is on this notion of induction, and so the idea with the model successor is borrowing from Peano's axioms, the notion of a successor function in that context, right? Which is that if I have some data set, D1, and then I was to run a successor function on it to create D2, the sort of harder instance of it, and I was to run that successor function again, then what I would be doing is increasing the complexity. And if I imagine this was like I don't know, my brain is not braining. If I was to, like a state machine, then it's like the complexity of the state machine. How many nodes are in it or something like this might be a proxy for that. So then there's a second question, which is the model that was trained on D1, and then the model that was trained on D2. I should have a successor function between those that would allow me to generate a model that would be able to work on D3. And so if I was able to make that transition here, then it wouldn't matter that I was continually turning the crank and coming up with more and more complex things. The model would be able, I'd have a process for generating such a model that was not collect all numbers to infinity in order to let my language model count to infinity. And so it's a bit more of a wish list, but we're trying to figure out what assumptions were built into the current paradigms, and by necessity, again, no shade at all. And does that help us kind of rethink this piece? Yeah, but I don't have a perfect answer to that.
Hi, Yonatan. Thanks for the great talk and also very entertaining talk. You showed mostly like failure cases. So I'm wondering if there's any success stories where like LLMs or multimodal LLMs surprised you the most, that they can really boost the performance. I was, for example, thinking of that one example with like turn the can upright, and now there's a banana, and LLM would clearly tell you like, here's a banana, you can't turn it upright, I know that.
Yeah, so absolutely. So yes, I think that something I didn't show, for example, if we go all the way back to the beginning, the semantic memory that we were constructing is very heavily informed by that, and then the, quote, reasoning that's happening over that graph is also very heavily informed by LLMs. Specifically, I think at the moment we're using GPT-5 for most of that. And so our current version of this so one of the things that we've been talking about is imagine that you take the entire city of Montreal or something like this, and you take street view from the entire thing, and then I want to ask questions about like, hey, I need to run some errands, I need to do A before B and C, okay, like what is the process of sort of doing that enumeration? And I think the agentic frameworks that we have and the LLM's knowledge about those kinds of cases are very useful and relevant here. The assumption about LLMs that I think is always sort of both good and then also concerning is LLMs assume you have a perfect encoder and a perfect decoder, aka a human. And in that context, everything's great. So most of these failure cases could be chalked up to that sort of API boundary where it's like, I got it pretty explicit, but not torques specific, not motor specific. And as long as I have a pretty intelligent system on the other side, or I have, not all web agents, obviously we've been discussing lots of very difficult cases, but if I have APIs that are well specified and well behaved, then that's an okay assumption. So the failure cases are more like, when am I breaking that? When is it that the token space of actions and the token space of the LLM no longer match perfectly?
Cool, thanks.
Yeah.
Thank you for the great talk. So I was just wondering how much of the robot failure you attribute to the software itself, like the memory reasoning, but how much do you attribute to the actual hardware of it? Because I feel like, what if LLMs itself are good enough, but the robots just don't have the amount of sensors, the amount of capacity like a human have?
Yeah, so 100%, but let me sort of try to formalize how I think about that question, because I think it's actually very similar to the one that was just asked. It's when do we have a semantic unit? Once I have a semantic unit, then attention mechanisms are great. Then symbolic reasoning is great. And then transformers and the pre-training and all that kind of stuff. But it assumes that I can do that. So let's say I want to add more sensors to my robot, which I definitely should. Robots basically don't have skin right now, so they don't have good tactile sensing, all this kind of information. So then they don't have they don't know what it feels like, or something like this. Okay. So now I have this little bit which is telling me the amount of pressure on every single one of my touch sensors that's happening at however many hertz, however many times a second, and I have this. Okay, I now have to turn that into something meaningful, and that is a huge ask. So one way to interpret the question is like, totally fine, I get you. That means that LLMs are good as my reasoner. And the real problem that I'm articulating is just that I need to figure out how to turn things into like a sufficiently abstract symbol in order to use LLMs. And I think that's totally fine. Personally, the reason that I moved from being a more traditional, I was originally a syntax guy. The reason I moved from syntax to robotics is because this issue of where meaning comes from feels like it's in the sensors. So if I don't have that sensor data informing my linguistic representations, then I'll never actually understand what any of those things are. I'll never really know what it means for something to be rough or for different grits of sandpaper or whatever else. I'll maybe, best case scenario, I have a vision thing that can sort of predict it, but then my generalization will be limited because I've only ever have one view, one slice, one sort of low dimensional version of it. And so I really want a situation where all of that information is being pushed in so that just as a human, the word rough, like rough sandpaper, like connotes all kinds of things. Or the idea of, how about the idea of licking sandpaper, like gives me a visceral, like, ugh, like that requires that I have sensed or that I can then generalize what it might be like. And I think that's missing if I'm just sort of assuming that LLMs are kind of capped out at this stage and sort of never have sort of a full end-to-end all the way from the bottom. But I'm totally open to a philosophical argument that is contrary to that.
Thank you.
Great. Okay, I think we'll wrap up there and go to lunch. So thank you, Yonatan.